receptor better than the pi tautomer. Let me put my phone silent. It's becoming a nuisance. All right. So I hope that is clear. So there is a reason why we are adding the sulfur. It is an electron withdrawer. When you look at butyramide, it has the alkyl groups. You have just these alkyl groups are electron donors, so they will be pushing electrons into the system, and they will promote the pi tautomer. When you add a sulfur, you promote the teletautomer and not the pi tautomer. And it is the teletautomer that we want. But you can see here, unfortunately, the meteamide was found to cause kidney damage and granulocytopenia due to the thiourea. So the next thing was again go back and replace the thiourea with the guanidino moiety. You return the guanidino moiety. So you have already had the insertion of the sulfur. So the next was to replace the thiourea with the guanidino moiety. Of course, the resultant molecule was less potent than when you have the thiourea, but it was safer. It was much safer. And then, as you can see here, we have said increased binding, reduced pKa of the ring nitrogen, and increase also and increased permeability. Once you reduce the pKa, that if you reduce the pKa, that means you are increasing the Ka. So you reduce the pKa, you increase the Ka. In other words, then this nitrogen becomes a little bit more acidic, and because the higher the Ka, the higher the acidity of the molecule. So this nitrogen is becoming a little bit more acidic. If it becomes more acidic, it means it's getting rid. Its nitrogens are not available for it to be protonated. If it is not protonated, the molecules that better penetrate the membranes are the non-ionized, and that is why we are increasing permeability. So kindly note, when you reduce the pKa, you increase Ka. When you increase the Ka, it means you are making this molecule more acidic. If it's becoming more acidic, it means this nitrogen is not protonable, because be more basic. This nitrogen is not protonable. When it is not protonable, then the ionization of that molecule is much reduced, and therefore it will be more concentrated in the non-ionized form, and that non-ionized form better penetrates the membrane than the ionized form. So I hope that you have understood that explanation. So from now, having done that, it was still not the final molecule. Now they worked now on this other final area. And what they did is that they put an electron withdrawing group there and reduce the basicity, but retain the polarity. So finally, you can see now our sulfur is there, our methyl is there. I've explained those ones. Of course, there's lengthening of that chain. That is a requirement for this drug to be able to bind the receptor properly. Then, of course, we have said there is change of the thiourea to the guanidino. And then after that, you see when there was, after that, change of the thiourea to the guanidino. On the guanidino, they added a CN. A CN is carbon, triple bond nitrogen. It's an electron withdrawer. This group is an electron withdrawer. It withdraws the electrons from the nitrogen, and therefore this system, on withdrawing electrons, it renders the whole of this system non-basic, because it's withdrawing electrons. Remember, for a molecule to be basic, it must have a lone pair of electrons, which it can donate, or which will facilitate it to bind a proton. But once this nitrile group, that's a cyanonitrile group, pulls away the electrons from the whole of this system, none of these nitrogens will be basic enough to be protonated. And therefore, the addition of the cyano group allows the whole of this molecule to have lower basicity, but the molecule retains polarity, because the nitrogen is polar, then the nitrogen, this other second nitrogen is polar, and that nitrogen is polar. So the whole of that section now renders this molecule to have low basicity and also to be polar. To have low basicity but to be polar, it allows this molecule to concentrate within the cell membranes or within the cell or within the body. It allows for the teletotomer to be the one which predominates. And once the teletotomer predominates, that is the totomer that will go for the H2 receptors. And that is the genesis, all the historical development of the historical development of the H2 blockers. So now, with that understanding, we can be able to go back. I wanted, first of all, to make you understand that explanation. So now, when we go back, you will now be able to understand what the notes are talking about. So we are saying we started with guanine histamine. There was extension of the side chain, which increased anti-H2 potency, but some agonist activity remained. So it increased. So that's what we want. So we are therefore saying side chain extension increases the H2 potency, but some agonist activity remained. So we still have an issue. Replacing the basic guanidino group with a neutral thiourea yielded effective H2 agonist. So the reason why first they changed guanidino to thiourea is to improve on the H2 antagonist activity. Then that is how we'd mentioned burimamide, and it lacked agonist action, but was not orally absorbed. That we did mention. And from there, they went into metiamide. One, addition of an electron withdrawer reduces the pKa of the ring nitrogen. And as we have said, once it reduces the pKa, it increases the Ka. Remember, this is a base. When you have a basic compound and you increase the Ka of that basic compound, it means you are making it more acidic. You are reducing its basicity. That's all we are doing. So we are reducing the basicity of the pi nitrogen, and in doing so, we are reducing its ionization. Ionization in terms of its ability to bind a proton. I mean, its ability to bind a proton and therefore bring. Remember, when these molecules binds a proton, you have an extra positive within the ring. So it reduces the ionization, it increases membrane permeability, because you have the molecule which is non-ionized being more concentrated, and therefore that increases absorption. It was more potent than burimamide. It allows for the teletotomer to predominate, which interacts with the H2 receptor. That's why I said, let me first look at the development, and now I hope the notes are quite, because this is what we have just mentioned. Unfortunately, this drug caused, as we have said, granulocytopenia, possibly due to the thiourea group, so it was replaced by the isosteric guanidine moiety. So this is just explaining why this was done, why that was done. The resultant compound, being highly basic, was 20 times less potent. So the guanidino moiety, because it is more basic than the thiourea, was 20 times less potent. Again, therefore, they went back to the drawing board. What can we do to reduce the basicity? And that is how they introduced the cyano moiety. And in introducing the cyano moiety, as I said, the cyano moiety withdraws the electrons, decreases the pKa, increases the Ka, reduces the basicity of the molecule, and therefore, and that molecule was the molecule we call cimetidine. And indeed, it had appreciable, it had good anti-ulcer activity, and is actually the prototype in this class. So replacement of this group with stronger electron withdrawer, but more lipophilic. So it was too good. It was lipophilic, therefore allowing the molecule to penetrate the membranes, but more lipophilic cyanoderivative yielded cimetidine. And indeed, cimetidine is our first molecule which was found, one, to have good pharmacological activity, and also to have minimal toxicity. So that's how cimetidine was developed. And then, of course, after cimetidine, because Cimetidine has had its own shortcomings. There was more structural modification to give the other drugs, the ranitidines, the nizatidines, and the famotidine. So there was more structural development to bring about the development of the other drugs. So now, again, this is just the illustration where we decide if we compare burimamide and metiamide in terms of their ability to form the teletotomer. We are saying when you look at this structure of burimamide, when we add a proton, of course, this is what I was saying, when you protonate this one, then the whole of this will become positive. And this can be protonated because when you have these alkyl groups, this alkyl group are proton donors. They are proton donors. And because they are proton donors, they will increase the basicity of the nitrogen. They will increase the nucleophilicity of the nitrogen. They will increase the decrease the pKa up because we want the Ka to go down, and therefore the pKa will increase. They will increase the pKa, making this molecule more basic. And once this molecule becomes more basic, because of this, we call it positive inductive effect, they will push the electrons into the aromatic system. That nitrogen will be more basic, and therefore that is why it can't be protonated. Once it's protonated, then you can't see, once this protonation occurs, the next thing is that you can lose this proton here, and once you lose that proton, then what will be in existence is the pi tautomer. So you will have the teletotomer and the pi tautomer in equilibrium, and we have already said that we do not want the pi tautomer. What we want is this, the teletotomer. It is the one which is preferable for binding the receptor. So that is burimamide. When we look at metiamide, we have introduced a sulfur. So here we have a positive inductive effect. Here we have a negative inductive effect. This sulfur will pull away electrons, and therefore this sulfur pulling away electrons, it will decrease the nucleophilicity of that nitrogen. It will make it less basic and more acidic, so it will increase its Ka, decrease its pKa, and in so doing, then you cannot be able to form the pi tautomer. You cannot protonate that nitrogen. Even if you protonate it, it will go back to the original one, which is more stable. So you try to protonate, you get to that, but instead of this protonated, instead of this cation forming the pi tautomer, it reverts back to the teletotomer, and therefore metiamide will have most of its drug existing as the teletotomer, and this teletotomer is what you require. That teletotomer is what you require to bind the receptor. The only disadvantage, as we have said, is this urea, which costs a lot of toxicity, and it has guanidino moiety, which again increase the basicity requirement for slightly more structural modification. So this is just what we are saying. That is what I've explained. So I don't need to explain it again. Don't need to go through this. I've explained it. It's what I've explained, that depending on the group that you have at position 4, if you have an electron donating group, it will increase the basicity of nitrogen 3 and therefore promote the formation of the. If you have an electron withdrawing group, it will decrease the basicity of nitrogen 3 and therefore promote the formation of the teletotomer, and that's what we want. And of course, also the methyl group or an alkyl group or an electron donor at position number 5 will do the same. If you put an alkyl group there, if you put an electron donor there, it will add the basicity of the nitrogen and again promote the teletotomer. And that is why when you look at the structure of cimetidine, number 5, it has a sulfur. Those two substituents are adding or are facilitating or are enhancing the formation of the teletotomer, which you do require for binding of the H2 receptor. So those two are very, very important because you require the teletotomer to bind the receptor. This is just what we have done. We have looked at. All you need to remember is the effects. When a group withdraws electrons from the main ring, when it withdraws, we say that is a negative inductive effect. It is pulling away electrons, negative inductive effect. When it pushes electrons into the system, it's adding the electronic characteristic. We call that a positive inductive effect. So the sulfur is bringing in a negative inductive effect, pulling away electrons from the emitters ring, and therefore favoring the teletotomer. Whereas when you have the alkyl group, it has a positive inductive effect, pushing electrons into the system, favoring the pi-totomer, and therefore not very good for binding the H2 receptors. It's the same thing that we had looked at. So that is this now we have looked at. I had to start there so to make you understand what we are talking about. So therefore, these are other drugs also. But as I said, we will concentrate on the 4. We are therefore saying cimetidine. That is the structure of cimetidine. And we can understand the structure of cimetidine. You can see that is our imidazole ring there. So it has a imidazole ring, and basically it has a imidazole ring. It still has this nitrogen, but of course that nitrogen is no longer a terminal nitrogen because we do have other substituents. So if you look at this cimetidine, it has an alkyl group there, a small methyl group, which we can understand. It has a imidazole ring for it to be able to go for the H2 receptors to retain the structural resemblance with histamine. Then there is this group here, the separator. So that spacer between the imidazole ring requires to be 1, 2, 3, 4. So that separator is 4 atoms with optimal activity. 4 atoms. We are talking about from the terminal nitrogen. We are calling this as the terminal nitrogen. The nitrogen which was previously in histamine. The separation of that nitrogen from the imidazole ring is 1, 2, 3, 4 atoms. We cannot say carbon because there is a sulfur, and that was found to be responsible for maximum activity. We have talked about this cyano group. The cyano or nitrile group was important. It introduces high lipid solubility. It also has negative inductive effect, pulling away electrons from that nitrogen, and even that pulling away electrons from the whole of this structure, the guanidino moiety, and therefore reducing the basicity of the whole of this structure, and that is what favors H2 binding. So that is cimetidine. It needs an aromatic ring. This is the aromatic ring there. With pi, this is the N is the same as pi nitrogens next to the side chain. The imidazole ring is not required. The other drugs, we will see that this imidazole ring can be replaced with other rings. It can be replaced with a furan, as in ranitidine. It can be replaced with a thiazole ring, as in famotidine, and so on, with retention of activity. So you do not need an imidazole ring. But when it is there, then the side chain you must have when it is present, that nitrogen must have, you have to have that nitrogen with pi electrons side chain, so that favors the formation of the teletotomer. So the imidazole ring is not required. The other H2 antagonists don't have it, but if it is present, the teletotomer should predominate, and the teletotomer is promoted by electron donors at position number 5, that promotes the teletotomer, and electron withdrawer at position number 4. So an electron withdrawer at position number 4 and an electron donor at position number 5 will promote the teletotomer, because we have already said that the teletotomer is the one which is responsible for binding the H2 receptors. The terminal nitrogen group should be polar but not basic. This we have said the cyano group has allowed, or the cyano group has reduced the basicity of that terminal nitrogen for maximum activity. Separation of the ring from the nitrogen group by 4 atoms gives us a maximum activity. You see a contradiction of this in one of the drugs which has 5 atoms but still with retention of a pressure-able activity. Cimetidine is an extremely successful drug in the treatment of ulcers. Note the electron donor, the methyl group at carbon 5, and the electron withdrawing side chain at carbon 4. Also the non-basic cyanoguanidine moiety or terminal nitrogen group. So these are the main characteristics of the side chain, or of the major characteristics of cimetidine for it to have optimal H2 blockade. However, cimetidine has several disadvantages. It is an inhibitor. In fact, we say cimetidine is a general. It's a low potency inhibitor of drug metabolism. So it is a general, in other words, not specific for specific cytochrome P450 enzymes, but it's a general but low potency inhibitor of most of the drug metabolism. And therefore, that is a big hindrance. It hinders or it inhibits some of the enzymes that are responsible for metabolizing quite a number of drugs. And that gives the cimetidine quite a disadvantage, because if you have a drug that has issues of drug metabolism, then you expect a lot of drug-drug interactions. So, however, cimetidine has several disadvantages. It is an inhibitor of cytochrome P450, which leads to many drug-drug interactions. The only advantage is that it is not high potency inhibitor, but nevertheless, it can still cause drug-drug interaction. It exhibits anti-androgenic action and can cause gynecomastia. In other words, in males, because of the anti-androgenic activity, it can cause gynecomastia in males. I believe you know what gynecomastia is. Further, it has 60 to 70% oral bioavailability. So some of these disadvantages, it has hormonal disadvantages. As we have said, it has anti-androgenic effects. It has that metabolic drug-drug interactions. These disadvantages prompted further structural modification to see whether there could be development of better molecules. And that is how the next drug, ranitidine, was developed. Ranitidine is the next drug. As we have said, if you look at ranitidine, you see this is now a furan. Okay. You see ranitidine, this is not an imidazole ring, but it's a furan ring. But you can still see one thing. It has that oxygen, which has in fact 2 lone pairs of electrons next to the side chain. So that rule, which we found in cimetidine, is still maintained. It is only that you can isosterically replace the imidazole ring with a furan ring with retention of activity. Again, see the sulfur still there, 1, 2, 3, 4 to the terminal nitrogen there. Then look at our group here. See this group here, you can see the NHCH3 is of course in both of them. Now instead of the cyano group, you have an amine ketene group. So nitroamine ketene group here. So this group here, you can see also the nitrogen. The nitro group is a powerful electron withdrawer. So again, this nitro group will withdraw electrons from the whole of this group and therefore reduce the basicity even as it maintains the polarity. Because remember, the nitro group is usually charged. There is nitrogen there. So the molecule has polarity, but there is reduced basicity and of course enough lipophilicity for that molecule to penetrate the receptors. There is addition again of this group here. 1, 2, 3, 1, 2, 3, 4, 5. At position 5 again, there is introduction of that group. This group will also push electrons into the system to allow, because here we do not have the teleonine, whatever totoma, but there's the only main use of this group is that it helps us to form salts. This nitrogen can be protonated, or you can protonate this nitrogen and you can be able to give ranitidine as the ranitidine hydrochloride. You can even be able to formulate it as an injectable because of the presence of this dimethyl amino group. So that dimethyl amino group helps in formulation of salts, of more soluble preparations. So that is ranitidine. Again, similar characteristics. We can be able to compare this with compound we have talked about, cimetidine. So it's a furan derivative, an isoster of the imidazole with, again, pi electrons of the oxygen. Again, 50% bioavailability. It is 4 to 10 times more potent than cimetidine with a longer duration of action. Further, it's a weaker. That's a very big advantage. It's a weaker cytochrome P450 inhibitor. The tertiary amine side chain allows for the formation of salts. Any question up to there? Any question up to there?